Alrighty, good morning, guys. Can you hear me?
Yes, I can hear you.
Are there any questions or comments before we get started? Okay. Then we'll continue with the conditional expectations. So last time we were talking about, we introduced and discussed these conditional expectations. Right, so you're given a random variable. It's f measurable. And then you're given a sigma algebra G, which is no bigger than f. And then we define this conditional expectation of x given G. Right, so that's going to be a random variable, just like x is, but it's going to have slightly different properties. It's going to satisfy that this object here, it satisfies the two properties. The first one is that while x is f measurable, the conditional expectation x given G is going to be G measurable. And the other property that it satisfies is that it's this partial averaging. And what that means is that when I integrate over sets inside the sigma algebra G, whether I integrate the conditional expectation or I integrate the thing I condition on, I'm going to get the same thing. And this is no matter what set I pick inside the sigma algebra G. So we proved existence and uniqueness when x is integrable. So what we're going to be doing now is we're going to talk about some of the properties that that the conditional expectation of x given g has. We're going to look at some examples, and then we're going to move into martingale. So today we're going to be looking at some properties, examples. Then we're going to look at the multi-period binomial model. And in here we'll have martingales. I'm also hoping that we'll have some time to talk about Markov processes. Okay. So you already played a little bit with this conditional expectation in your homework. So let me just discuss some of its properties. We'll look at another example. So some properties. Well, it's linear. It's a linear. The conditional expectation is linear. Right, so the conditional expectation of ax plus by given g, you can write this as a given g plus bx given g. So if you take two random variables x and y, take two constants a and b, then the conditional expectation of that sum, I can take constants outside, and I can write the sum of the conditional expectation of sum into the sum of conditional expectations. If y is already G measurable, and say that the conditional expectation of the product xy is finite, well then, if I am to compute the conditional expectation of x times y given g, right, this is, to be able to write down this conditional expectation, we only know that that exists under this property, so that's why we have that property. Like x up here is given, x is, if measurable, the expectation of x is finite, and g is something inside f. So how can I compute this? Well, if y is already measurable with respect to g, then that y can travel outside. If you take h inside g, so take another sigma algebra that's potentially even smaller than g, where remember g is already inside f. That was a property up here. If you do that, then you can look at iterated expectations. Iterated expectations. And it's this property where you say, well, conditional expectation of x given g. This is going to be a g measurable random variable. So I could take something smaller and condition. So we'll take the conditional expectation of the conditional expectation. And what that's going to be is, so you have g and h here next to each other. It's the smallest one. Pen died. The smallest one wins. The smallest one is h. And as an example, you're going to get this unbiasedness of conditional expectations. So if I take h to be the trivial sigma algebra, so I only have omega and I have the empty set. This is the trivial sigma algebra, the smallest sigma algebra in the world. If I take that one, then I'm just going to get expectations up here. I'm just going to get that the expectation of x given g expectation, this is exactly the expectation of x. So you see, this is, if we're thinking about this conditional expectation of x given g as an estimate of x, then when I talk about an estimator being unbiased, what that means is that this estimate has the right expectation, and having the right expectation means that the expectation of the estimate is exactly the expectation of the quantity you're trying to estimate. So this equality here, this shows that the conditional expectation seen as an estimator is unbiased. It has the correct mean. Other property is that if x is independent of the sigma algebra G, so what does it mean for a random variable to be independent of a sigma algebra? That means that if I look at x, I'm going to get independence of these indicators. So x is independent of the indicator for G for any set inside the sigma algebra. If I have that structure and I'm interested in the conditional expectation of x given G, any guesses on what that conditional expectation is going to be? I'm trying to estimate x given something that has nothing to do with x. What would be my estimate? Very good. So that's going to be the expectation. What else do we have? We have Jensen's inequality. We have Jensen's inequality. So now we need a function. We'll have a function which is going to be convex. So this could be like the puts and the calls. It could be k minus x x minus k. We've seen those. Those are convex functions. And so if I have when I have that the expectation of the random variable f of x is finite in absolute value, well then I get an inequality. I'm going to get that. I'm going to get that the conditional expectation of f of x given g has a relationship to f of the conditional expectation of x given g. Which one is biggest? Jensen's inequality, so this is just a little trick. So a trick to remember Jensen. You test, you know this is going to work for convex functions. So you test it out. You test with f of a just to be the square function. So then you want to know is how do these two relate to each other? Which one is biggest? So you can't remember if it goes this way, which one is bigger? Is this one bigger or is that one bigger? And this is what you're in doubt about. So test with this to figure out what the relationship here is. And this is of course a convex function, right? This is a square function, that's convex. I'm going to test with this one, and then you're going to use that the variance of a random variable, you know that that's always positive. And you also know that it's given as the expectation of x squared minus the expectation of x, everything squared. So there you have it, because now we can move this term here. Now we can move this term here to the other side, and you get that this is what has to be true. So if you're facing a problem with a convex function, one way to remember Jensen's inequality is you test it out. You test it out with like a specific function where you know it's going to be true, and then that the way that inequality is in this specific example, that's going to be the case for the general function that's convex. Which is just a trick to remember which way to put the inequality. So Jensen's inequality says that if I'm interested in estimating a convex function of x given g, well then you have a bound. So if you go back to your homework, that bound was actually in your homework. So if you have a look at example to this here was from homework. So we had, so in class we did the case when we had this e of x given y, and you were jointly normals, and we computed this thing here to be rho y. Remember we did that last time? These are jointly normals. And then in your homework, you were asked to compute basically the same thing, but with an exponential function in a way. So what would that be equal to? Well, so you could use Jensen's inequality, right? Because the exponential function is convex. So if you use Jensen's inequality, if you use Jensen inequality of a convex function, you pull the convex function outside, you're going to get something here which is bigger than, and then you have e to the conditional expectation of x given y, which you know what is from what we did in class. This is e to the rho y. What you actually computed, what you had, or you should have, instead of getting the inequality, you actually computed what this thing here was. Does anybody remember what it was you got? You got something with the e rho y. And then what did you get over here? What did you guys get for the conditional expectation?
Was it minus what is f(x)?
Something like half times the variance of something. Anybody remember what you got?
I think it was like another thing that was independent from f.
Yes.
Or y in this case.
Yeah, it's independent of y, and so you needed that variance to come up here. Remember what the variance was? Something like 1 minus rho squared.
1 minus p squared.
Yeah, and t is equal to 1, right?
Oh, yeah.
Yeah. And do we have a plus or a minus here?
Minus?
You have a minus here? Or a plus?
I don't know.
You have a minus or a plus? I think it's a plus. So we should do a sanity check, right? This here is what we're claiming that the left-hand side is. So just a sanity check. We need to have e to the rho y plus 1/2 1 minus rho squared. We need to have that this is bigger than e to the rho y. And so is that true? No, and we can cancel out. Is this bigger than 1? Yeah, it is, because rho squared is less than or equal to 1. So we have a positive number here. Right, of course, it has to be true, right? That's why it's called a sanity check. It's just to make sure we didn't mess up. So for example, have we put a minus sign here? Have we put a minus sign here, and we'll go through the calculations, we'll come down here, and we will not have this property, right? If there's a minus sign over here, this is not going to be bigger than 1. This is going to be less than 1. So this is kind of another way to just do a little calculation after you're done solving the problem, just to make sure that what you have doesn't violate something obvious, like violating the inequality in Jensen.
Hello. I want to ask about this question.
Yes.
Can I open my camera?
Of course. Yeah.
Let me change my. I write it like this. I write it like this. I write it like this, and others is here. It's here. It's here. I wonder why. I wonder where I made the mistake.
Can we try to do this in office hours? Did this, I think.
Okay. Okay, I will go to your office hour.
That would be awesome. Yeah, are there any questions about what we have on my piece of paper up here? So that was, those are some of the properties of conditional expectations. How do you calculate them? There's this one tool that comes up quite often. And it's called the independence lemma. So the main tool for calculation at this point, so a main tool for calculation is called the independence lemma. And what it says is, so this lemma you'll find in both textbooks. Here I have the thin book, and I just looked it up before class, and it sits up here. It's over here on this page. This lemma here, and there's a corresponding lemma in the thicker book. So when we refer to the independence lemma, it's this result here that I'm referring to. And let me write it down, because this has been confusing in the past. And yeah, let me see if I can try to avoid some of the confusion that I've seen in the past. So you take a function. Let f go from R2 either to the positive or be such that you have integrability. I'm going to take absolute value, or want to have f from R2 to R such that when I integrate the absolute value, I'm finite. Right, so either you have that it's positive, or you have that this property holds. Then there's a formula for how to compute a conditional expectation. And the formula is that you compute the conditional expectation of x, f of x comma y, given y. This conditional expectation, this can be computed. This conditional expectation can be computed by computing an unconditional expectation. So I'm going to have here that x is independent of y. Two random variables x and y. I want to compute a function of the two and a condition on one of them. There is a formula for how to do that. And the way that you do it is that you compute an unconditional expectation of x, and then you replace y, the one you condition on, by a dummy. And you calculate this expectation. Now you're going to get a function of the dummy. And when you're done calculating, you put the dummy to be y. So our textbooks divide this expression over here as g of a. Divide this as f of x comma a. So we define this deterministic function, and then g of y is this conditional expectation of f of x comma y given y. So my instead of taking you guys through the proof, I would rather try to take you guys through how one would actually try to calculate using this independence lemma here. Right, so the point is that if you have two independent random variables and you want to compute the conditional expectation of a function of the two given one of them, you can basically do that by computing regular expectations and then evaluating those regular expectations at a random variable. So let me try to show you how one can do that. So this is another old exam question. If we take x and y, the normals, standard normals, the standard normals, the independent. So then what I'm interested in is computing. I'm interested in computing the conditional expectation of an exponential of, say, b times x times y. So I'm going to take a constant, and then I want to compute this conditional expectation given, say, y. Right, we are in the case, and my function is the exponential function, so it's positive. It falls into the first category. This is positive. So there's a formula for this. And so what it says is that you should write this, you can write this as an exponential of b, and then you take out what's known. So this is x, you replace y by a dummy. Let's call it dummy for a. And you compute this, and when you're done computing it, you put the dummy to be the random variable y. So what I have here is now Gaussian. So we have that formula, which we actually just used. This is the moment varying function for the normal, evaluated at a times b. So this here is equal to, and these are standard normals, so the variance of x is equal to 1. The mean is equal to 0. So I'll get here, this is an exponential of 1/2 ba squared. And when I'm done computing, I put a equal to y. And now there's no more expectation. I'm done computing. I'm going to get that this here is equal to the exponential of 1/2 b squared y squared. We can also see, we can then, for example, we can use that, we can use the unbiasedness of expectations, and just say that I can figure out what the mean now is. So I could ask a question like, if I am to compute the expectation just of the random variable e to the b times xy, I can use this iterated expectations. And I can say that this is the same thing as the expectation of the conditional expectation given y. Which I figured out. This is equal to the expectation of e to the 1/2 b squared y squared. So if I want to know, for example, I want to know when is this thing finite? This is finite if and only if that this quantity is finite what kind of b's will give me a finite expectation here? Well, this will be the same thing. I have an expectation, y is standard normal. I can integrate out in the standard normal density. Say little y squared, and then it's e to the minus 1/2 y squared y. So this is the same thing as what would be. What kind of restriction do I get on b? When is an integral of this sort here finite? Question is, I'm starting out with two standard normals, x and y. First, we started out computing the conditional expectation of this exponential bx. We got down to here. And now I'm interested in knowing, here I have the unconditional one, right? There's no conditioning here. Here, up here, there was a condition. Here I'm interested in, when is this expectation finite? And you see there's a parameter b over there. What values of b give me a finite expectation? Okay, so this is just an application of, this is just to show you guys one application of this iterated expectations, namely that this expectation here is the same thing as taking the expectation of the conditional expectation. So what values of b give me something finite? Smaller than 0? No, this is too harsh. This is too harsh. You can get away with, you can do better than that. Well, you gotta be looking at what's inside here. I have plus 1/2 b squared. I have minus 1/2. So the critical value is gonna be when b squared is equal to 1. When b squared is equal to 1, what am I gonna get inside here? Well, when b squared is equal to 1, these two terms, they cancel out, and I integrate a 1 here. When I integrate 1 over r, I'm going to get plus infinity. So that doesn't work. The condition is that b squared has to be less than 1. Okay. This here is something that's going to come up in this. Here's a use. This is going to be useful in homework. I think it was homework 6. Let me just show you guys. So when you see it, I just put up the new homework yesterday. In this problem number 2 here, you have exactly this scenario that we have. Like, you have x and y, the two independent standard normals. You take a constant, and now you can see this constant is restricted to be strictly less, such that this constant is strictly less than 1, which is the condition we just found. And the reason that you do that is because down here you're dividing by this expectation. Right, so without this restriction up here, this expectation down here would be plus infinity, right? So you would not have something that is strictly positive. So now you know why there's this restriction here on sigma squared being, why sigma squared has to be strictly less than 1. Okay, are there any questions on this sheet of paper? Any questions about? So the independence lemma, we're going to be using that quite a bit. So my notation is that this here means you look at this expectation as a function of a, you compute what the expectation is, and then you replace that dummy here. You replace this dummy here with the random variable. Why b squared less than 1? Well, you see the exponent in here is, if you combine the two terms, these two terms here, right, you become e to the 1/2 y squared, and then you'll have b squared minus 1. So for example, if b squared is equal to 1, if b squared is equal to 1, then it's going to be the exponential function evaluated at 0, which is a 1. Right, so if b squared was equal to 1, say, then you would integrate 1 over r. If you integrate 1 over r, you're going to get plus infinity. So b squared equal to 1 does not work. You need to be smaller. Right? If b squared equal to 1 doesn't work, then b squared equal to 2 is also not going to work. You need to be smaller. Right? And so if b squared is strictly less than 1, then this term here dominates. And you're going to be integral. So you find the critical case. The critical case is b squared equal to 1. So if you're less than, you're going to be finite. If you're bigger, then you're going to be infinite. And then you check the critical case by itself. The critical case by itself also leads to plus infinity. So this is an example of a moment generating function. Right? This here is our moment generating function. For x times y, right, evaluated at b. So this is an example of a moment generating function that is not finite for all values of b. And this is one of the reasons that I don't like them, is because they can easily become plus infinity. And here you indeed do, right? You have x times y, the product of two normals. Product of two normals is going to lead to moment generating functions not being finite everywhere. Okay, let's try to move on. Let's go. Let's get back and try to do some. Let me just make sure I didn't miss something. Let's try to get back and do finance. Try to apply this material multi-period binomial model. So we're going to multi-period binomial model. Multi-period binomial. So what you start out with now will be the size you want to have. you either have, if it's an n period model, you'll have an n up here, or if you have an infinite number, these are going to be IIDs, Bernoullis. You're going to be IID coin flips. And so coin flips, right, so I have my psi n. It's going to take on two values. It's either going to be u or it's going to be d. It's going to go to u, and it's going to become u with probability p, and it's going to be d with probability 1 minus p. So the stock price process, this is defined recursively. So you're going to start out by some initial value, say it's positive. And then you're going to get, so that's the initial one, and then you're going to get, the recursive formula is going to be that Sn plus 1, this is defined as the previous one, times psi n plus 1. So if you want, you can expand this out. You're going to get that this is psi 1, psi 2, all the way up to psi n plus 1, the product, times S0. So that's the stock price. And of course, you're going to have a bank. The bank is just the same. You start out, let's just start out at 1, and then you're going to get the bank price at time n plus 1. This is equal to the bank price previously times 1 plus r. So as before, you'll have these input parameters r and u and d, and you're going to have the same relationship as before. You're going to have that. What are you going to have? You're going to have that u is bigger than 1 plus r, which is bigger than d. This is the no arbitrage condition. So we're going to have that again. And we're probably going to have, we want to have positive stock prices. So we're going to keep d, this one here, this is just positivity. And so you're going to start out with these random variables. I denote them by psi, and the IID, so the independent and identically distributed, and the coin flips, Bernoullis, these coin flips here. Some people call them for Bernoullis. The Bernoullis, you take on the only two values, u and d, and you take it on with probability p and probability 1 minus p. So then we're going to form a filtration. So we're going to move into now the material that we've been building up the last couple of times. We're going to look at a filtration. So I'm going to denote that by Fn. The filtration is going to be the sigma algebra that makes S0, so that's a constant, S1, S2, all the way up to Sn, measurable. And of course, if you want, this is going to be the same as making psi 1, psi 2, all the way up to psi n measurable. So the filtration, which we know we've had filtrations before, we have here that Fn increases in size as we move into the future. Right, so Fn plus 1 has more information than Fn. And we can start computing, and we can compute quantities like an expectation of Sn plus 1 given, say, Fn. If I want to do that, well, now we have the tools to it. I know what this random variable here is about. This random variable here is it satisfies the properties. It's going to be measurable with respect to what I condition on. Right, so this thing here is going to be Fn measurable. And it's going to satisfy the partial averaging property, which means that if I take sets inside Fn now, and I integrate the original random variable, which is Sn plus 1, or I integrate the conditional expectation over those sets, this guy, over sets inside Fn, I'm going to get the same value. And to compute it, well, the way that we do that is we use the formula, we plug in. This is the expectation of, then you have Sn here, and then you have your psi n plus 1. Use the formula given Fn. And then we start using some of the properties that we listed. One of the properties that we listed was if you have a product and one of them is measurable, you can pull that measurable random variable outside the expectation. Like this y here was measurable with respect to g. This y here can then be pulled outside the conditional expectation. So we'll do that. So I'll have outside here, we'll have psi n plus 1. Conditional expectation of Sn given Fn. Okay, so what about here? This was wrong. Sorry. Sn is Fn measurable, so I can pull Sn outside. And then inside here, I'll have my psi n plus 1 given Fn. The wrong thing I pulled outside. Sn is measurable with respect to Fn, so I'm left here with psi n plus 1. Now we're going to look for another property that we had listed, namely that if the random variable is independent of what I condition on, if I'm independent of what I condition on, the best estimate is just going to be the unconditional expectation. So here I'll get what? I'll get Sn times the expectation of psi n plus 1. But now not conditional. Right, so the first thing I used for this one, here I used that Sn is Fn measurable. And for this one, I'm using that psi n plus 1 is independent of Fn. That's where I'm doing, this is where I'm using the independent, and so I'm using the independent. I'm using the first I here. So when I'm looking at psi n plus 1, and I'm conditioned on knowing the first n coin flips, these two things, the unrelated, the independent. So here I just have the unconditional expectation, and I can use the identically distributed. I'll get here that this will be p times u plus 1 minus p times t. So this is the expectation. This is the conditional expectation of the stock price at a future time point given event. We could iterate this. We could iterate. So we could do, for example, that the conditional expectation, we could be interested in the conditional expectation at time n plus 2 given Fn. Right, we could put in put in another gap in here. Okay, so we'll do that. Then how would that work? Well, we will take, we'll use iterated conditional expectations. So we'll put in an extra conditional expectation in between. So this is going to be Sn plus 2, but instead of conditioning on Fn, I'll condition first on Fn plus 1. And then I'll condition on, well, Fn. Right, so what I'm doing now is I'm using another one of these properties that we had listed. I'm using this property here that if I have two H and G, and I do the iterated conditional expectation of first condition on G, then a condition on H, then it's the smallest one that wins. Right, so here I have Fn plus 1 and Fn. It's the smaller one that wins, so that's going to give me Fn. But the one on the right-hand side is much easier to work with because this is what I just computed. Right? This will be the conditional expectation of, so I'll just use this formula here with n equal to n plus 1. This is Sn plus 1 times Pu minus 1 minus P times D, condition on Fn. And so now here I have a constant. You have a constant, so I'll pull the constant outside. Pu plus, this is a plus 1 minus P times D. I'll put it outside. Sn plus 1 given Fn, which is also what I just computed. So I'll plug that in. Conditional expectation of Sn plus 1 given Fn. It was the mess that we had up here. Sn plus 1 given Fn. Same formula. I'm going to get the same term again. So I'm going to get now a square out here. Times Sn. Any questions so far? So we're now working in a multi-period binomial model. And we're trying to compute some conditional expectations in this multi-period binomial model. We also had, in the binomial model, we also have other probabilities. If we're looking at the risk-neutral probabilities, the risk-neutral probabilities, these are, so I'm still going to have my size to become U, to become D, but now I have a P tilde here and I have a 1 minus P tilde here. P tilde is equal to, I hope we remember the formula. So this was 1 plus R minus D divided by U minus D. So if I take the formula, for example, if I take this formula here, but I want to compute it not under the P probability, so I don't have P's here, but I want to put P tildes, what would I get? So then I will have that the conditional expectation, now under the tilde probabilities of Sn plus 1 given Fn, it will be the same as what we had here, just with tildes. This will be Sn times P tilde U plus 1 minus P tilde and D. And then I get this idea that I could divide by 1 plus R. So I divide by 1 plus R on the left-hand side. Of course, I'll have to divide by 1 plus R on the right-hand side. first formula did nothing else than take what we had before, but put tildes everywhere. And now let's work out what the right-hand side here is, because we have a formula for p tilde. I have this formula for p tilde. I want to plug it in here. Plug it into this. This is 1 plus r. I get my Sn. Inside here, what do I end up with? I would have something like p tilde. Then it would be u minus d plus d. And my p tilde is up here. So you see u minus d is downstairs in p tilde and is upstairs here. So you'll cancel out. I'll get 1 plus r Sn. P tilde becomes 1 plus r minus d plus d. And so the d's cancel, 1 plus r here, 1 plus r down there, it cancels, I get Sn. So this is a curious property, right? I condition Sn plus 1 given Fn, I divide by the interest rate, I get Sn here. So we should also recall these different prices that we talked about. So recall when we introduced AD securities. Recall when we introduced AD securities, we used these discounted prices. Discounted prices were the ones that has a tilde on top. So S tilde n, the ones that we used back then, they were Sn divided by S0n. So we divide by the bank account. Right, this is equal to Sn divided by 1 plus r to the nth. So if I look at, so I'm computing under the tilde measure, I'm computing Sn plus 1 tilde given Fn. So what will I do is I'll take the formula. I take the formula for the discounted market, plug it in, pull the constants outside, 1 over 1 plus r to the n plus 1, e tilde Sn plus 1 given Fn. This is the one we have an expression for. This is the one we have an expression for. If I take 1 over r, compute all this stuff, I end up with Sn. So I'll borrow 1 over r from the front. Here I'll get 1 plus r to the nth. And then this will give me Sn. Right. I had n plus 1 out here in the front. I borrowed one of them, so I could use this formula. It will give me Sn. All this stuff here was equal to Sn. I'll replace that 1 over 1 plus r times this conditional expectation with Sn. And this here is exactly Sn tilde. So we have this curious property that says that the conditional expectation of the stock price at the next time point, given what we know now, is exactly the current stock price. And this is not far away from your homework. Recall your homework. So recall the homework. You were looking at the conditional expectation of S1. And this was exactly equal to S0. This was the trinomial model. Remember you had this property in the trinomial model? But that's very, very similar to what we have up here. There was no interest rate in the trinomial model, so we will just have the tildes and the not tilde prices would be the same. So apply this formula here with n equal to 1. So n is equal to 1 and r was equal to 0, then you'll see that what you had in the trinomial problem is consistent with what we just found here in the more general case. This property here that we're seeing, that you compute the conditional expectation at a later time given what you know now, and you just get the current value. This is a defining property of a martingale. So this is quite important. So definition, let me call it, let me say that, so a process, Mn, or if you just have a finite one, if this is a martingale, if, so I should write out martingale, is as a martingale, if, well, the first one is that Mn is Fn measurable. This is also called being adapted. This is Fn measurable for all n. 2, needed to be integrable. And then the conditional expectation of Mn plus 1 given Fn. This is Mn. So we have these properties, in particular the third one, that when you try to condition on future information, when you try to condition the random variable at a future point, given current information, you just get the current value. That's the martingale property. So as an example, discounted stock prices, these S tilde n's, Sn divided by dr martingales under P tilde. Are there questions on the last few pages of paper that I wrote up? So maybe we should just go over it like one more time. We're playing now, we're moving into a setting that has multiple time points. And so we're keeping track of time using this variable little n. So this little n here, this is going to be helping us keep track of time. So we're moving into a setting that has multiple time points. And so a stock price process is then something that is random and it evolves over time. It starts out somewhere, and then as time goes, we flip a coin. At every given time step, we take the stock price that we had before, flip a coin, and multiply up. This here is a multiplicative. This is a multiplicative. It's multiplicative because of this structure here. This is a multiplicative model. So we now have a stock price that evolves over time. Every time you get a new coin flip, you're going to get twice as many possible values, right? Because you're going to go from Sn, and then you're multiplying onto a random variable that takes two different sets. So what you want to get here is you'll get this model structure. Okay, and then we'll keep going like that. So then now we have a dynamic structure, dynamic because we have multiple time points, and so we can introduce filtration. The filtration is the sigma algebra that is being generated by the previous stock prices. So up to time n, we pretend that you can observe the current stock price and the previous ones. Right, remember this notation here. What that means is, this here means that, I'll just write this over here on the side. Like what this means is that Sk is Fn measurable for all k between 0, 1, 2, all the way up to n. Right, so this is the smallest sigma algebra that makes all the stock prices, all these random variables measurable up to time n. And of course, there's a relationship between the stock prices and these coin flips, right? This is a constant, so that doesn't matter. You can either include him or exclude him, that's okay. S1 is equal to S0 times xi. Right, so the sigma algebra that makes S1 measurable is the same thing as the one that makes psi1 measurable, and so on. So that's the filtration. It's a filtration because it's a sequence of sigma algebras that are increasing over time. Right. So this here is what makes it a filtration. And so we can then start computing conditional expectations given these sigma algebras and see how they move over time. And so there was one here. We compute the conditional expectation of a future stock price given what we know at time n. We did our calculation, then we iterated it. This is something you'll see quite a bit. You iterate forward, and then you use iterated expectations. If you have in between time n plus 1 and time n, you can put in time between time n plus 2 and time n, you can put in that time point n plus 1. And now there's just one time step between these two, and one time step between these two. And so what that allows you to do is basically reuse the one time step calculation you just did, and you get something like this. We also introduced these risk-neutral probabilities that had a very specific form, and we're now rediscovering why they are called risk-neutral probabilities. They have a martingale property. This here is why they are called instead of risk-neutral probabilities, we call them martingale measure. We call p tilde for the martingale measure, because it has this martingale property. Are there questions on this? Now is a good time to ask before we move on. Any questions on what we just did? should look at another example of the martingale just to be sure we have some relationship to what it means to be a martingale. So a very large class of martingales can be constructed as in this example here. So there is a example, and these martingales here, they are quite famous. They call Lec5A martingales. The Lec5A martingales, what you do is you say let A, this is going to be a random variable, let A be a random variable. It has to be integrable, so I need to be able to compute the conditional expectation of A, an absolute value, and get something that is finite. Then, if I look at Mn, this is going to be defined as the conditional expectation of A given Fn. This object is a martingale. Excuse me. This is a martingale. So I take a random variable, any random variable that has this property, and it's integrable, I get a martingale out of this. And the proof, it is deceivingly simple. We have three properties to satisfy. We check. We have property number one, it says that you have to be measurable. You have to be integrable, and you have to have this conditional expectation property. So you need to go 1, 2, and 3. You have to satisfy those. And are measurable, that's okay because this is part of the conditional expectation. This is Fn measurable. If you look back to one of the very first slides of today, where we were told, like, what was it that a conditional expectation had to satisfy? The conditional expectation had to satisfy that it was measurable with respect to the sigma algebra in which you condition. So this here must be Fn measurable. Okay, so that was property one. Property number two was that I have to be able to compute the conditional expectation. You have to be able to compute the expectation. So the expectation of absolute value of Mn, I need to prove that this is finite. Okay, I'll plug in what the definition is. And then what? How do we get this thing to be finite? Well, I have an absolute value function. I have the absolute value function sitting outside the conditional expectation. Could I put it inside so that I will get it in here? Could I move the absolute value inside an expectation? Let me ask this question, are these two the same or are they different? Is the absolute value of an expectation the same thing as the expectation of the absolute value? That's correct. Hoshi is right. So if they're not the same, Is there a relationship between them? Can I say that one is bigger than the other? If so, why? Yeah, so the answer is at the absolute value, there is a bound. And who gives us this bound? Well, let's recall, I agree, I like the triangle inequality, but remember what we had here, right, was I know what the expectation is without any functions, and then I take an exponential function. If I have the exponential function inside, I get something that is bigger than when I have the exponential function outside. That's because the exponential function is convex. Right? So convexity gives us this inequality. Well, and that inequality has a name, right? This is Jensen's inequality. As soon as you have convexity, you get an inequality. Okay, so what is the function? So here we had this was the exponential function, right? The exponential function is convex. Right, this looks like a convex function. I pick any 2 points here. I pick any 2 points on in the domain. I put a straight line. All the points on the straight line are above the function points. Okay, so they're not convex. What do I have over here? I have the absolute value function. So I look at the absolute value function. It's this guy. Okay, so I take any 2 points, this guy and this guy, put it in a straight line. Are the points on the straight line above the function points? And the answer is yes, I'm convex, and it is. So now I have Jensen's inequality. Jensen's inequality says that you get something bigger when the convex function is on the inside. Convex function on the inside, here's on the outside, here move it in. This is Jensen. This was Jensen. Jensen says that this here is good. Then I have the expectation of a conditional expectation. I have an expectation of a conditional expectation. I know what that is because that was one of the properties. That was another one of the properties that we had talked about. If I look at an expectation of a conditional expectation, an expectation of a conditional expectation, I just get the unconditional one. Okay, so the expectation of a conditional expectation, this is equal to the unconditional. And this was what was assumed to be finite. That was our assumption up there. And the third property is that if I take 2 time points, so let me take mn plus 1 and condition on fn. Right, I want to prove that this here is mn. Okay, so what I do is I plug in mn plus 1. This is the conditional expectation of a given fn plus 1 given fn. This was the definition of mn plus 1. I just plug it in. And then what do? I now have 2 next to each other. I have fn and fn plus 1 just sitting side by side. What I do is I know that the smallest one wins. The smallest one, fn plus 1, the smallest one wins. This is a given fn. And this was my mn. The smallest one wins. This is going to give me It's going to give me Mn. And these are the three properties that I needed to check. And that shows that martingales, this is what I have up here. This shows up in many different contexts and settings. So typical places where you'll find stuff like this is, so typical places where this shows up, it include pricing. Include pricing. So if I take a function, this is my derivative pricing. So I'm interested in computing a conditional expectation of f applied to say s n. I want to compute either expectations under the tilde measure, and then I want to condition on fn. This here is a this is a martingale. This is a martingale under p tilde. It also very often comes up in the theory of Radon-Nikodym derivatives. I think the textbook even has a name for it. It's a Radon-Nikodym derivative process. Let's make sure I got that right. Yeah, that is exactly what he calls it. So we are in the first textbook. He has devoted a full chapter, chapter 3.2. It's called the Radon-Nikodym derivative process. Okay, so here's what that is. You look at the conditional expectation of the QDP given fn. And he called this one here for Zn. And this is a martingale. This time we're computing expectations on the P. These are two examples where this particular structure comes up. So you need to note, so just some warnings. Maybe just one warning. So sometimes you'll see, maybe it's just one warning. So often you see something like an expectation under this tilde measure, and then inside here there'll be something like f. There'll be something like f of much like what we have up here of Sn, but then sometimes you're being thrown for a loop, and it does something like there'll be 1 plus r, and then maybe something like n minus n down here, given fn. So now this doesn't work, and this is not a martingale. Right, so I'm putting a line on the not a martingale. And the reason for that is because you need to look for the ends. Right, there's an n here, and there's an n here. So there can be no n inside the expectation. So when stuff like this happens, watch out, because if there's both an n here and you condition on that n, this won't work. So this here is not a martingale. Whereas if I looked at the conditional expectation of f of Sn divided by 1 plus r to the n, capital N, given fn, this is a martingale. So no n inside the expectation is allowed, if you want the martingale property. And this, unfortunately, is something that comes up quite often. It comes up both in continuous time, it comes up in discrete time finance. Very often the things that you need to compute, you're like obscured by this n here appearing in multiple places. So look out for that. Here we're good. The little n only appears on the right-hand side. It does not appear in here. Little n is just out here. It's not inside there, and it works. These martingales we saw on slide 13, they are specific cases of this general class of martingales called Debye martingales. Okay, I think this is a good time to take a little break. Let's take a 10-minute pause, and then, as usual here in the morning, we have to change Zoom link. So switch over on the other Zoom link, take a little break, get a new cup of coffee, and then we'll do the other half of the lecture after the break. Okay, I'll see you guys in 10 minutes.